Hello, this is lecture 4 of lecture 15. So it's part 4, I should say, of lecture 15, fourth video. And we've talked about friction. Now what I'm going to do is I'm going to put a lot of what we talked about together and talk about forces acting on multiple objects in a given situation. And I'm actually going to ignore friction for the first few cases, although we could add it in later. As a matter of fact, one of the homework problems on the next homework set puts friction into the hanging block problem, which is the one I'm going to do right now. Okay, so imagine you have this scenario where you have a block on a table. It's attached by a string over a pulley, which you used in lab, to a hanging block. And I'm going to say that this is the mass of the hanging block, and this is the mass of the block on the table. We actually saw something like this in lab. I think it was the fourth lab. Way back when you did forces and friction a little while ago. All right, so in this problem here, what I want to do is I want to consider all the forces acting on both blocks, and my goal is to determine this block's acceleration. Okay, that's what I want to do, is figure out what is that block's acceleration going to be. So how do I do that? The way to do that is to look at Newton's second law for both blocks. All right, so the first step in this problem is to find the forces acting on all blocks. And in the end, I'll have an equation that you can just use. But this process is important in case there's other forces that we're not considering in this case here. You might have to go through this step, this procedure to do this when I add another force in, like the force of friction, which I'm going to ignore right now. All right, so let's go ahead and sketch the forces acting on both blocks. I'll do this in a different color. I'll do it in red. So if this were class, I'd ask you how many forces are acting on each of these blocks. If you want to take a moment, think about that, pause the video, go right ahead. For those of you who don't, I'm just going to show you what the forces are. This block has two forces acting on it. One of them is the force of tension caused by the string that's pulling the block upward. The other one is the force due to gravity that's pulling the block downward. And of course, we know how big that force of gravity is. Whenever I say Fg, in your mind you should be saying, oh, Fg is the object's mass times gravity. In this case, the object's mass is the mass of the hanging object here, so it's mh times g. All right, so that's the force due to gravity acting on this object here. This one up here, how many forces does it have? Well, there's tension pulling it this way. It also, of course, has gravity. And this one has the normal force. This one does not have a normal force because it's not resting against anything. Nothing's pushing on it. This one does have a normal force, the normal force of the table pushing on it. And it also has the force due to gravity. And that's going to be the mass of the block on the table times, times g. Sorry about that. Okay, so they both have the force due to gravity acting on them. I'll distinguish them. And they both have the normal force acting on, they both have the tension force acting on them, and this one has the normal force acting on it. Okay, so I've tracked all the forces, I've gotten them all. And now we'll go on to step 2. What would I do in this situation? I would apply Newton's second law to both blocks. Okay, so I'm going to apply Newton's second law to both blocks. And what does that mean? That means applying F net equals ma. All right, so for this block here, I'll say the net force acting on that block, I'll call it the block on the table, it's equal to the block's mass times the acceleration of that block, which I'm going to be looking for. For this one here, I would say the net force acting on the hanging block equals the mass of the hanging block times the hanging block's acceleration. All right, so let's look at what must be the net forces acting on both the block on the table and on the hanging block in terms of the forces that I've listed for each of them. Well, for the block on the table, the force due to gravity and the normal force are going to be canceling each other out for reasons we've been discussing this semester so far. But the tension force is going to be the leftover force, or the net force. So for this block here, it's going to be the tension force. I can say, okay, this is the tension force. That's equal to the mass of the block on the table times A. For this block down here, I have the tension force acting on this block and the force of gravity acting on that block. Those are the only two forces acting on it. They can't cancel out because the block is going to be accelerating, so there actually is going to be one that's bigger than the other one. But the difference between them is going to be equal to the net force acting on that block. So I'm going to write that out here. I'm going to say, okay, for this block down here, I have the tension force pulling up on the block minus the force due to gravity pulling down on the block. That's equal to mass times the acceleration of the hanging block. There. All right, I'm going to erase some of this extra text here. Okay, now the third step, so I applied Newton's second law to both blocks, and I got this equation. You make the t a capital T so it's consistent. And I have that equation. These are the two equations I got by applying Newton's second law to each block. Great. Now the third step is to identify like terms in both equations. What are like terms? Well, things that are the same. That's what I mean by that. What's the same? Well, you saw in the third law lab that if you have tension, with two objects pulling each other, kind of like a tug of war, even if you have a pulley in there, the tension should be the same for this object that it experiences by tension as that object experiences by tension. So these tension forces are the same. That's useful to know. The other thing that is useful to know, and I'm just going to make sure that we know that that's the acceleration of the block on the table, and this is the acceleration of the hanging block. Since these blocks are connected, they have to have the same acceleration, with the difference being that when this one's positive, that one's going to be negative because it's pulling it down. So here's how I'm going to write that. I'm going to say, okay, the acceleration of the block on the table is equal to negative the acceleration of the hanging block, which is equal to, and I'll just say that this one, I'll call it A, and I'll say that that one is minus A. Okay, so this one's going to experience an acceleration of A. This one's going to experience acceleration of negative A, negative times what that one is. Okay, so how I'm going to write that then, I can simplify these equations a little bit. I'm going to erase a lot of this stuff. I hope you got it down. You can always rewind the video if you didn't. But I'm going to erase a lot of this. And I'm going to rewrite these equations with those simplified expressions so that I can then solve the equations. I can put them together and solve them. Two equations, two unknowns, and I'll find my acceleration, which is what I'm looking for. So here's what I'll do. I'm going to say, okay, this Ft equals mt times A. I'm just going to leave Ft alone. It's the same Ft in both equations. You just need to remember that. This one down here, I can say Ft minus Fgh equals minus ma. Now I have this, since this ah is equal to minus a, I'm going to put that minus in front here and just have the a right there. Okay, so now what I have here is I have two equations, and this should be mh, by the way. It's the mass of the hanging object. But I have two equations and two unknowns. I'm assuming that I know the mass of the block on the table and the mass of the hanging block. So I'm not going to call those unknowns. This here I'm going to know because I know it's the mass of the hanging block times g, and both of those I will know. So what I don't know is the tension force in the string, and I also don't know the acceleration. I'm going to solve for the acceleration and see what I get. So I'm going to simplify these equations and solve. I'm going to remove some of this text here so I can do that work. And what I think I'll do is I'll do a substitution. Wherever I see an ft here, I will put mt times a. So I'm going to substitute. And I'm going to get, okay, I'm going to get mt times a minus fgh equals minus mh times a. So notice I got rid of my tension term by substituting this expression here in my tension right there. This went away, it became that. Now I can solve for a. I'm going to bring this a over to here. I'll bring fgh over to there, and I'll rewrite everything. So I'll write that out there. Write this out here, plus mh times a. And I'll also add fgh to both sides. I'll cancel that, this cancels that, and then I'll add fgh over here. Okay, so I'm going to rewrite everything that I just did, and I'll put it up here. And I'll say, okay, I have mt, that's the mass of the object on the table, times the acceleration, plus the mass of the hanging object times acceleration. That's what's on my left side. That sum is going to be equal to fgh. That's the weight of the hanging object. And if this were class, I'd ask you, what is the weight of the hanging object? And you would say, it's the mass of the hanging object times g. Remember that. So I can rewrite this and say mh times g. That's the weight of the hanging object. These two are equivalent. This is going to be equal to mt times a plus mh times a. All right? I'm going to erase a whole bunch of this stuff so I can write my final equation here. I'll rewrite what I just did, and I'll solve it, and then we'll have this nice expression for acceleration. So I'm going to rewrite this. I'm going to say, okay, I have a times mt plus mh equals mh times g. Divide both sides by mt plus mh. And here's what I have. I have acceleration is equal to mh divided by mt plus mh times g. All right, so that's my equation for acceleration. I'm going to stop this video. It's already 13.5 minutes long. And in the next video, I'll do an example of this, and then we'll do the Atwood machine, which is a lot like this.